Section 3.2 is Rolle's theorem and the mean value theorem. We could just call this section the mean value theorem. What Rolle's theorem is a special case of the mean value theorem, but it's the easier case, so that's the one we usually start with and talk about. Rolle's theorem says the following. Suppose that f is continuous on the interval ab, that's a closed interval, and differentiable on the open interval ab, and f of a equals f of b. Then there is a number, c, between a and b, such that the derivative at c equals 0. Okay, so continuous, you guys know what it means. We're not going to have any jumps, no holes, no. We're not going to have any asymptotes. The sharp turns we're going to not get as well because of the differentiable comment, right? Differentiable means no sharp turns. So this is going to be something that's nice and smooth and connected, right? And it has this additional condition, this is the additional condition for Rolle's theorem, that the endpoints on the interval match.
What is that little...
Which one? Oh, yes, this means, this symbol, thank you for asking, means is an element of. What it means for this in particular is that it's saying that the C lies between A and B. It's somewhere between them. It's an element on that interval. It's a number between A and B.
Could we just say that? Like it's between...
Yeah, you could. You'd be totally fine.
Are you going to have to write any of these definitions?
I'm not going to require you to write this definition on the test. No. But you do need to know the conditions that it sets forth. So we're going to have to check every time 3 conditions. 1, it's continuous. 2, it's differentiable. And 3, the endpoints match. If you do not have all 3 of those conditions, you know, the hypothesis, then you can't guarantee the conclusion. Okay. Just like in science, right? If the hypotheses are all messed up, we're not going to have the conclusion guaranteed.
Okay, just the polynomials.
What?
Does it work only with polynomials?
It doesn't work only with polynomials. It works with other things as well. But polynomials, for certain, it would work for, right? Because they do have these conditions. At least they have the first 2 conditions. The third one they still might not have in some cases. It just depends.
Okay.
Now, in terms of a graph, the picture of what this looks like, that's important. So you've got something, like we said, where it's nice and smooth. And it tells you that the endpoints are the same y value. Okay? So if this is A and this is B, then what it's telling you is that it's smooth, it's continuous, and we have the endpoints match. Now, I drew it this way because this is kind of the only thing that can happen. There may be more curvature between them, but somewhere in between it has to stop increasing and start decreasing. Otherwise, it can't get back to the same y value, right? Of course. And so Rolle's theorem says that what that means is that there is some location between there where I have a horizontal tangent line. I have a slope of 0. I have a turning point. Right.
Yeah.
It's not only with parabolas. Even Mooney asked, is it only with polynomials? And the answer is no, it's not only with polynomials either. Think about graphs of sine and cosine. Wouldn't they have some of these features if we set the endpoints correctly? Sure. Even other graphs will too if we set the endpoints correctly. So just hold tight to the idea that this is very narrowly focused. It is not a narrowly focused definition.
Or can you just change interval?
Yes. If you have certain intervals work and certain intervals don't. So we're going to try an example. Determine whether Rolle's theorem can be applied. Now that's a really important condition. All right, you have to actually show that it meets all 3 of those points that we said we labeled 1, 2, 3 on the previous slide. The cool thing is, if it fails one of those, you're done. So do not skip this step. Occasionally they will fail, right? And then you don't have to keep going because then you'll be searching for something that may not exist. And boy, would that be unfortunate to spend time searching for something that didn't exist, right? Yeah, definitely. So we're going to consider all 3 of those conditions, make sure that they apply. If those theorems apply, then we're going to find all of the values that we do in fact have the derivative equal to 0. All right? So, and then if Rolle's theorem cannot be applied, we're going to explain why it can't. So, our first condition that we're supposed to check is that it's continuous. Why is this one continuous? Yeah, this one works because it's a polynomial. Polynomials are always continuous. We learned that back in chapter 1. Second condition we're going to check is it differentiable? Do you remember why? Yeah, same reason, right? And we learned that in chapter 2. This one is differentiable because it's a polynomial. Okay, polynomials are nice because they have both those conditions and you sort of get them for free when you're explaining what works. The third condition is the condition that is very specific to Rolle's theorem. It's checking that the endpoints match. What are the endpoints that they give us on this interval? I mean, what is the interval they give us? Yeah, it's 0, and 3. So we need to check to see that this works. How do I check to see if f of 0 equals f of 3?
You plug it in.
Yeah, you plug in 0. So literally what I have is negative 0 squared plus 3 times 0. And I'm checking to see if that's equal to negative 3 squared plus 3 times 3.
0.
So on the left, I get 0. On the right, I get 0. I don't even care if I get 0. I just care that I get the same thing. Okay, there's nothing special about the fact that this happens to be 0. What's special is that they happen to be the same. Okay, so yeah, this worked. So, yes, so Rolle's theorem applies. Because I've satisfied all of the hypotheses, all of the conditions that I had to satisfy. So what that means is that I'm going to be able to take the derivative of this function, set it equal to 0, and find a solution. So, what is the derivative of this function? Fantastic. And can I set that equal to 0 and solve it? Of course I can. What will I get?
3 over 2.
3 over 2.
Yep, 3 over 2. You guys got it. 3 over 2. Now, let's say for a moment, and the case will happen eventually later, that I got 2 or 3 or 4 answers. Maybe I get more than just one, right? And even just getting this one, I need to make sure that the answer I'm getting is located between the endpoints. Because that's what Rolle's theorem says is supposed to happen. Not just that I get one, but that it's happening between 0 and 3. Yeah?
Does it have to be directly between like?
No, it does not have to be halfway. And in fact, most of the time it won't be. This one is because it's a parabola and it's symmetric, but most functions won't have that symmetry involved. All right, so is this value between?
Yes.
Yeah, it is. So this is the C value that I was looking for. So C is equal to 3/2. What if I had an answer that was C is 3/2 and C is 5? Yeah, I would mark out the 5 as being my C value. It would be an X value that would work, but it wasn't the C value I was looking for, right? You could have 2 between them, absolutely.
Like C equals 3/2 comma
2. Yep, absolutely possible. All right, a little bit more interesting of function. This one is not a polynomial, right?
Oh, no.
So you cannot say it's polynomial for any of the reasonings of anything, correct? All right, so number 1. I'm supposed to check if this is continuous.
And positive.
And we have to make sure we're looking on this interval, because sometimes things are not continuous in general, but they might be continuous on a particular interval. So it would probably be helpful for you to take a look at a graph. Make sure that you don't see anything weird going on as a starting point, because this is not a graph you're probably very familiar with. So take a look at the graph. You're going to put in y into y1, you're going to put in x to the 2/3 minus 1. And you want your window to go from -8 to 8. Now, there's not going to be any x values I'm not allowed to have, because this is to the 2/3. And if you're familiar or if you remember, what this means is the cube root of x squared. That's what 2/3 means as an exponent. So I can put in any x value I want. That's not a problem. But you have to check for both the continuous and the differentiable. So on your graph, what do you see?
There's like what's that?
Yeah, there's a cusp in the graph, right? So we need to make sure that we identify why it fails. This is going to fail because of that cusp. Which condition does it fail?
It's not differentiable.
It's not differentiable. So the continuous is fine. That's no problem. The second one, and you can just justify this with a graph, which would be a good idea. The differentiable, it fails.
Did you say not differentiable because of the cusp? It has a cusp.
Yeah, it has a cusp, it has a sharp turn, whatever of those two pieces of language you use. Where's the sharp turn?
0, negative.
Yeah, at x equals 0, or you could identify the point 0. You say -1, Fallon?
Yes.
Okay.
Looks like it.
And so the Raleigh's theorem will not apply.
So that's technically your answer, is that it doesn't exist.
Well,
And then for that reason.
it's not that it doesn't exist, it's that we don't know that the conditions, well, let me say it this way. The hypotheses are not satisfied, so we don't know that the conclusion will hold. So could there still be this point C between the two that has the derivative of 0? There could, but this theorem does not guarantee that there will be. And that's what we're actually trying to check the conditions for, is whether or not we can actually say for sure this theorem can be used, and it can't, because this one is not differentiable at x equals 0. Now, pause for a moment and think with me. What if the interval we were given was the interval from 1 to 8?
It would be. Okay.
Right, we'd have to go out and check the endpoints, right, and still see if that would work. But the differentiable part would be okay, correct? So the reason this is falling apart with the differentiable is because the point where it's not differentiable is actually between the two endpoints we're looking at. So those endpoints really do matter, because they could, there could be an asymptote in your graph. But if the asymptote's not between your two endpoints, then it doesn't matter, right? It's all about the interval we're looking on.
So you only look at that right half of it?
Exactly. You only look at that half or that portion that it references in your interval. Okay, same directions, trig function, sine graph, all right? So first condition is continuous. What do you think?
Yes.
Yes.
Do we have
This
to
is continuous.
Justify it like if you give us this on the test, or can we just say yes, it's continuous?
You're going to say, just like we're writing down right here, you're going to say it's continuous, and the reason is because it's a sine curve. Don't say it's a trig curve, because some trig curves are not continuous, correct? Can you give me an example of a trig curve that's not continuous? Tangent. Go tangent, yeah. Okay. Second one, differentiable.
What was our reasoning for the last example of why it was continuous?
It's continuous because it's a cube root, actually. Cube roots are continuous. Square roots wouldn't be unless you're only dealing with positive values. But since this is a cube root, you can put positives or negatives and 0 into cube roots without a problem. Yeah.
Okay.
All right, this is differentiable, yes? Why?
Yeah.
Because it's a sine.
Yeah, I know it feels like we're sort of reiterating, but we actually had theorems that said this back in chapter 2 and chapter 1. We had theorems that said if you have a polynomial, if you have a sine curve, it's continuous. If you have a polynomial, if you have a sine curve, then you have a differentiable function. So we're citing theorems without actually saying theorem, 2.7.6 or whatever they were, kind of thing. This is because it's a sine curve.
Would a cosine curve work too?
Yes, it would. Sine and cosine are the two trig functions that are so super friendly that we get to use lots of features that polynomials have, actually. Third condition. What is the third condition? We didn't actually have to test that on the last one because we fell apart before we got there. The endpoints. We need to test and see if f of 0, in this case, equals f of 2 pi. All right, so this is our sort of our question. We're testing this. So f of 0 means sine of 0. And f of 2 pi means sine of 2 pi. What is sine of 0? It is 0. Cosine of 0 would be 1. And sine of 2 pi is 0. Yeah, so these check out, right? So since we have the 3 conditions, Rolle's theorem applies. Fantastic. So we've satisfied our hypothesis. What are we going to be able to be guaranteed will happen in our conclusion? The derivative will equal 0 somewhere between 0 and 2 pi. So what's the derivative of sine x? Cosine of x. And now you're back to that unit circle kind of issue, right? Where does the cosine of x equal 0? Yeah, very good. I wondered if you would notice that. It equals 0 a lot of places, right? But these are the only 2 locations that are between 0 and pi. 0 and 2 pi. So our c values that we are guaranteed to find, we actually found 2 of them this time. They're actually not halfway in between. So we saw an example of that you guys asked about. They're at pi over 2 and 3 pi over 2.
Would that look certain on a graph?
You're just going to have 2 locations where it ends up. So this graph looks something like this without putting in 2 more details. The endpoints match, and we have 2 locations where we have slopes of 0. And that makes sense because it's the sine curve, cosine curve. It's at 1/4 of the way and 3/4 of the way. Yeah. Yeah, it has to do with the period of the function. Okay, we're generalizing now. Mean value theorem. You will notice the conditions of the mean value theorem start out very similar to Rolle's theorem. We have a function f that is continuous on AB, and it's differentiable on AB. Continuous on the closed interval, differentiable on the open interval. So those 2 conditions are the same. But what do you notice is not there?
The f from c equals 0.
That's true, but before that, I mean with the conditions, Fallon. Yeah, the endpoints do not need to match on this one. So we have fewer conditions at the beginning, right? Fewer conditions at the beginning. What we are guaranteed now, instead of having that the endpoints give, or that the derivative is 0 somewhere between, we have that the derivative equals this thing that says f of b minus f of a over b minus a. And you've seen that somewhere before. That looks a lot like the limit definition. It should look a lot like the formula for slope. y1 minus y2 over x1 minus x2. Okay, so these are not sort of coincidental things, obviously. There's a reason for that. So let me draw you a picture that justifies the reason for what's going on here. Oh, let me make one comment before I do that. If, in fact, f of b equals f of a, what would happen to the right-hand side of this equation?
0 on the top.
It'd be 0 on the top.
Yeah, 0. Yeah.
So if the endpoints actually did this, wouldn't this say at the end f prime of c equals 0, just like the other problem did?
Yeah.
Yeah. This is why this is just a more generalized example of Rolle's theorem. Or you could say Rolle's theorem is a specific case of the mean value theorem. Okay, so let me show you this because this is a cool picture. And this is the picture that for whatever reason people forget about when they get to the test. Don't forget this picture. So I'm going to draw the picture like this. We've got some function. This is f of x. Here's my endpoint A, and here's my endpoint B. And I'm drawing them on purpose so that they don't match, so that I can show you how this picture looks different when they don't match. The right-hand side over here says I can calculate the slope between my 2 purple points. You know you can do that. That's a college algebra kind of concept. I mean, that's an algebra 1 kind of concept, right? We can calculate slope between any 2 points. So if I were to calculate that slope of those purple points, I would be calculating the slope of this line, right? here's my line. I can always calculate the slope of that line. What the mean value theorem is saying is that there is another location between A and B that would have the same slope. In particular, if you can imagine drawing a parallel line over here, roughly like this.
Just a tangent.
It's a tangent line. We are definitely drawing a tangent line, but they're saying there's a tangent line on our curve that has the same slope. Now, what I want to talk about before we quit today, don't go put anything away just yet, because I want you to write this down, is that this is a very good example of mathematics in the real world that is used by police officers. Okay? So let me give you an example as to why. So let's imagine that you're driving down the road, and there's a police officer at exit 15, and then there's another police officer at exit 25. The police officer at exit 15 knows what time you passed him, and the police officer at exit 25 knows what time you passed him, right? I mean, they can find out what time you're passing each one of them. And they can calculate your average speed between them, right? Simple mathematics. That's not even like calculus. That's just, arithmetic almost, right? Calculate your average speed. Well, if the average speed that you have gone is higher than the speed limit, then that means at some point between those two locations, you were in fact speeding. It's the only way for that to possibly happen, right?
True. Yeah.
That's exactly what this is saying. That purple line is the average, in this case, my example, speed. And the red line is actually the point when you were traveling the average speed.
They're smarter than
And it has happened, and it has been used in courts of law. Nobody has to clock you going 75 miles an hour to know that at some point you went 75 miles an hour. In fact, not only that, but they know you went beyond 75 miles per hour. If they could also clock you at mile 15 and mile 25 and knew that you were traveling the speed limit at both those locations, then at some point in between there, you were traveling much faster than 75, right?
Right.
Yes, you were. So this is actually a really cool one that has direct application into court. Like, how cool is that?
that is kind of
Okay.